Good afternoon, everybody. Before going into our plenary lecture today, I have a couple of announcements to do. The first one is that, as I mentioned yesterday, today at 18:15, we will have in 3 different places that you can check in all the screens in the main hall. We will have different meetings to inform you about the way in which the timing and all the details for the field trips from tomorrow. And then remember that following what is an IAS tradition, we will have here today a public lecture that is addressed to in the local language, so it will be in French. So we will have in this room at 18:15, starting at 7 p.m., this presentation, so don't miss it. And then I think I will pass now the floor to Judy McKenzie that will introduce our guest speaker today. Thank you. Judy.
Thank you, Daniel. I'm very pleased to introduce the second plenary speaker of the 19th International Sedimentological Congress, Professor Isabel Montañez. And for Isabel, this is kind of a homecoming. For those of you who don't know it, she is a citizen of Geneva. She was born in Geneva. And it's kind of a return of the native. So we're very pleased to have you with us. You don't have to give your speech in French, though. However, Isabel spent much of her childhood and her education was in the U.S., and she graduated with a doctorate degree in 1990 from Virginia Polytechnical Institute in Blacksburg, Virginia. And I believe your thesis was under the direction of Fred Reed. Yeah, many of us carbonate sedimentologists highly recognize the name Fred Reed. And Isabel then afterwards took up a position at the University of California in Riverside, first as an assistant professor and then associate professor. However, she moved on, but staying in the University of California system, she moved in 1998 to her present position as full professor at the University of California in Davis, California. Isabel's research interests are in the sedimentary record, and she couples that with the physical and chemical variations in paleoceans, global biogeochemical cycling in marine and terrestrial records, and carbonate fluid rock interaction in sedimentary basins using stratigraphy, petrography, and geochemistry, including stable isotopes and radiogenic isotopes and trace elements. Her laboratory research focuses on the development of quantitative paleoclimatic proxies and their applications for major or abrupt climate changes in the geological past. And moreover, and I heard this morning, somebody was upset. They happened to make a remark. I'm only a geologist. I'm still a geologist. But Isabel considers herself to be a true field geologist. There's nothing wrong with that, Isabel. We need geologists. Isabel has received many honors and awards throughout her career, among those being the James Lee Wilson Award for Excellence in Sedimentary Geology from the SEPM in 1996, and more recently she received a Guggenheim Fellowship between 2001 and 2012. I think she's going to be reporting on some of the work she completed during this fellowship time. Furthermore, she is a elected fellow of both the GSA and the American Association of Scientists, AAS. Her record of professional service is exemplary, and I think it's interesting because she has balanced between the European or the international IAS and SEPM. She has been a co-editor of Sedimentology from 2002 to 2006, and she was followed this by a stint as a editor of the IAS Special Publications, 2006-2007. She is also currently the co-editor of the Sedimentary Record, which is the publication of SEPM. And she's an editor on the editorial staff of Basin Research. So you really keep your service balanced between the two sedimentological societies, the largest ones. Isabel has been invited to give a number of distinguished lectures, such as the Ingerson Lecture of the Geochemical Society in 2012, and the SEPM keynote speaker at the AAPG meeting in 2013 in Pittsburgh. And I just happened to attend that meeting, listen to her talk, and I thought this would be a wonderful talk to present to the community here. So we're moving once again from SEPM to IS, and please welcome Isabel, who's going to tell us about the Earth's Deep Time Insights into Our Climate Future. Isabel, please.
So thank you, Judy, for a phenomenal introduction. I don't think I've ever had one quite so special. And thank you also to you and Daniel, Elias, and Rosanna for the opportunity to share this lecture with you. J'essaierai de présenter ça en français, mais c'est mieux si je fais en anglais. So it will be in English. And that's better than my Spanish, unfortunately. So every talk should have a primary message. And my primary message today is that the Earth's deep time geologic record provides a unique contribution to the climate change discussions. And what I mean by that specifically is that it is the deep time record, the sedimentary record, that uniquely archives how our Earth system will function in an evolving CO2 world as one that we heard about yesterday and you hear about today, and that we project that we'll go into. And as Carlotta introduced yesterday, the reason behind this is that this past spring we hit 400 ppm atmospheric CO2. The last time we saw that was 3 million years ago in the Pliocene. And we're probably pretty soon going to leave that 400 level. And by the end of the century, really all estimates at this point converge on levels that we haven't seen for the last tens of millions of years. So what I hope to convey today is that these are not analog worlds, and Carlotta made that point yesterday, but they do uniquely archive, and the emphasis is on processes in the climate system and how they respond to a changing and high CO2 world, one above 400 parts per million. But before I go on, I do want to say that I'm the sole author up here on this, but a lot of people have influenced what I'm going to say, and I'm going to present the work of others. And in particular, someone in this room, Lynn Sorgan from the University of Oklahoma, could just as easily be giving this talk. So let's start with where we are today in the recent past as a context for Earth's longer-term history. And you all recognize this as the Keeling curve, CO2 over the last 58 years. Here we are today at 401 parts per million, levels that are higher by 35% than the last 800,000 years at least. What should definitely be maybe the point of interest at most with this is the rates at which this has been changing in the last couple of decades. 2 to 3 parts per million per year. And in fact, at this point, it's 3 parts per million per year, and probably rising because of the influence of the onset and acceleration of those longer-term carbon positive feedbacks that we don't typically think about when we talk about climate change. Now, this is a curve you also, I'm sure, recognize, CO2 for the last 4 glacial interglacial cycles. When CO2 was low, we're talking about 180 parts, 200 parts per million. Ice sheets in Europe and in North America expanded far into those continents. And then when CO2 rose to levels still below 300 parts per million, the surface temperatures went up 3 to 5 degrees, and those ice sheets retracted considerably. You no doubt recognize this exponential rise that breaks this natural pattern, that of the last 150 years, and here we are today. But what is far more challenging to try to constrain is where we're going. And most recent estimates, including the latest IPCC, are converging for various economic emission models on a level of about 650, some are quite higher, plus or minus 100, 150 parts per million. But don't lose sight of, if we were to burn through the fossil fuel reserves that we know we have, the estimates are actually more like 1,000 to some estimates even as high as 2,000 parts per million within the next century or so. So I, like probably some of you in the room, ask the question, which is how far do we have to dial back that clock in geologic history to have an understanding of these kinds of levels of CO2? And so what you're looking at here is 60 million years of CO2, our best estimates based on marine and terrestrial proxies in red and green, respectively. Atmospheric CO2 on the vertical axis, the best estimate trend line in black. And then up here is the time span of our existing ice sheets on Earth. And I'm going to superimpose some orange shading, which is that predicted for our near-term future based on, again, all these different economic emission scenarios. And you can see two things from this. I probably don't even need to point them out, but I will. Firstly, if you look at where that intersects those lines, it means that we could be going back by the end of this century to levels we haven't seen since 34 million years ago. That 34 million is a key number given that it is prior to the onset of our stable ice. Just as interesting is the fact that when we look at the magnitude of carbon that is being emitted, these emissions are of geologic scale, things that would take normally tens to hundreds of thousands of years to accumulate, but are accumulating in a geologic instant. And that's going to kind of be the key theme here. It's all about rates and what we've learned about that and what we should think more about. Just to drive home that point that we have to go past the Pliocene to be able to understand how we'll function in this world. Here is, for example, CO2 and how it oscillated over the last about 1 million years. Pliocene may have gone to 435. All right, so we all know that we live in an ice house. This diagram from a paper recently by Parrish and Sorgen shows ice house times in blue, times where we have ice in the high latitudes that wax and wane. But maybe you do or don't appreciate that it is actually times, greenhouse times, shown in yellow in this diagram, that are the more prevalent climate state. Now we know that from lots of studies that those greenhouse times are characterized by elevated CO2. And this diagram is just one that recently came out for the Eocene late Cretaceous. It's based on quite a few different proxies as well as geochemical models. And the first thing I could say as an aside is clearly this illustrates how we definitely need to refine our quantitative estimates of CO2. But it says for sure that those values are elevated, probably in the range of at least 500 to 1,000. And what can we learn from that? Well, the point is that in contrast to the short-term and small-scale variability of our recent past, when you look at greenhouse times or times even in ice houses where CO2 is forcing climate under elevated values, it gives us an opportunity to really test those fundamental assumptions behind first-order controls on Earth's surface temperature and on climate sensitivity. And secondly, it allows us to test the strengths and the weaknesses of these climate models that are making all the projections you hear for the future, and where they work and where they fail. So on that note, the next 3 slides, I'm going to discuss this latter issue. Here you see latitudinal temperature gradients for the Cretaceous and the early Eocene. And I'm going to point out a couple of things, but I think you can immediately see that all of the proxy estimates, mostly from marine different proxies, fall well above the present-day latitudinal distribution. First thing that you see is that the tropical temperatures may have gone as high as 30, possibly 40 degrees. And this brings into question this notion that we held on to up until the very recent past, where we have some sort of a thermostat that maintains our tropical temperatures, buffers them, and clearly that is not the case. Perhaps even more alarmingly is that we look at polar warmth, values that go up to 10 degrees, 16 degrees minimally for mean annual temperatures, temperatures that allowed the expansion of forests into the Arctic, the proliferation of freshwater plants in the Arctic, and crocodilians in this region. You all know, I know you all know, I can see it in the titles of talks and posters, that this discrepancy between models and data remains one of the largest challenges in paleoclimatology. And despite recent efforts in models, they're getting closer when they use unbelievably high levels of CO2. They still cannot reproduce the warmth in the high latitudes when they have to come up with these levels of tropical warmth. So these next two slides, courtesy from my collaborator Chris Poulsen, a climate modeler, shows Cretaceous mean annual surface temperature for present-day CO2 and 10 times CO2. And what you see in the dots are how the models are doing relative to proxy data for those places and times. If it's orange, it's too hot. The model's producing too hot temperatures. Blue, too cold, and white, just right. And you can see that there's only one red dot, lots of blue dots at both of those levels. When you crank up CO2 to 16 times present day, which latest records of CO2 are suggesting no way did we reach, you're looking at still those blue dots in the high latitudes, in particular the continental interiors. So what people like Chris Poulsen and I take from this is that there are either issues with the physics of the models that we still are having issues with, and or there are processes in the climate system, for example, acceleration of long-term feedbacks, positive feedbacks, that we don't fully understand and that many of the models don't currently include. So clearly reconciling this has to be a high priority. Now to illustrate this sort of insight that can be gleaned from the deep time sedimentary record, I'm going to use 3 case studies. And I'm going to start with the PETM, or the Paleocene-Eocene thermal maximum, which has long been believed to be the analog for our future. Then we'll go on to the Triassic-Jurassic boundary in the Mesozoic, and to the late Paleozoic Ice Age. And all of these saw greenhouse gas forcing of climate. The issue is, though, it was all different for each of those cases, and clearly the boundary conditions are different. But I'm trying to make a point about this. These are not analog worlds. However, all the studies in these and other types of time periods have shown that the fundamental information or understanding we get on processes in the climate system and ecosystem response are transferable across climates. And depending on what the process is, it's transferable across timescales with relevance to our future. So the PETM, quickly, most of you know about the PETM, but you can't not bring it into this kind of discussion. This is a diagram showing benthic O18 of foraminifera, 60 million years. What I'm showing here is in this box. This is shows the rapid excursions in O18 that were superimposed on the extraordinary warmth of the early Eocene. These are known as hyperthermals. The Paleocene-Eocene thermal maximum, with PETM, being the perhaps largest magnitude and the first of the Cenozoic, 56 million years ago. Now, we've all seen lots of diagrams of the PETM. I do want to illustrate here, these are both from the marine records, deep sea cores. This just illustrates that even though temperatures on average went up about 5 or 6 degrees, in some places, in particular in the high latitudes, the temperatures went up much higher. In this case, this is from the algal biomarker Tex 86. The cause behind this, a massive injection of carbon to our oceans and to our atmosphere. That led to amazing greenhouse gas forcing. It's seen around the world on the basis of this very sharp negative isotope excursion. Seen also on land in terrestrial carbonates. Here it happens to be in the carbonate of tooth enamel of mammals from the Bighorn Basin. And people have shown that the oxygen isotopes, for instance, here of that tooth enamel carbonate correspond with 1-for-1 with the changes in carbon, just illustrating that this was a global warming directly related to that ejection of carbon to the atmosphere. But what I really wanted to make, main point I wanted to make for the PETM was the rate issue. So if you've kept up with the literature, you're probably aware that there's been a lot of controversy over how long this ejection of carbon to the atmosphere and oceans actually took place over. And what you're looking at here then is carbon release rate on the vertical axis, duration on a nonlinear scale on the x-axis. Here in black is projection for the burning of all of our fossil fuel reserves. Does not include methane hydrates, for instance. And then for the PTM in red under different scenarios. And the first thing I'll point out is the range of carbon that was emitted for the PTM runs anywhere from about 3,000 gigatons to about 9,000. So the value for today would fit right smack kind of in the middle of that. But what is really interesting is that the duration of the PTM, although it probably happened in pulses, perhaps with one major initial pulse, it still probably happened over about 20,000 years, and even longer if there was the acceleration of these positive feedbacks, which is what pretty much the data are all showing. So when you translate that to rates, we're looking at rates of emission to the atmosphere per year that are an order of magnitude, minimally smaller than that of our present condition. Translate that to temperature change, and that's what this bottom diagram does. In red is projections for our near-term future, about this rate, or this level, about 4 degrees. It's what the latest are suggesting for even 2100, versus what we see for the PETM. And now we're talking 2 orders of magnitude differences. So this fails as an analog. We don't have an analog world. And many of us would say that doesn't matter, because we have a lot to learn from process. So hyperthermals, we've heard a lot about hyperthermals in the Cenozoic, but hyperthermals go way into the Mesozoic. In fact, some are arguing that the Permo-Triassic boundary was probably a hyperthermal that just became more complex. And the largest magnitude hyperthermal of the Mesozoic is arguably that at 201 million years ago, the Triassic-Jurassic boundary. This, in terms of ecological impact, it was the 3rd largest of the 5 big extinctions. Some have shown that, for instance, 4 groups of giant reptiles went extinct, arguably opening up the pathway for the age of the dinosaurs. Plants, this is what I want to focus on here. Plants, 80 to 95% of the species went extinct. But like plants do for almost all perturbation, at the higher taxonomic order, they actually are pretty resilient. And the TJ was no exception. So what you're seeing here is dioramas showing the major floral turnover, but lack of total extinction in East Greenland. But in the late Triassic, the flora were dense, diverse gymnosperm forests, and afterwards they were swamp-like, much reduced canopy, and lots of ferns, sort of your weeds or cheap vegetation. This is the cuticle preservation in these, and this has allowed for CO2 estimates to be done based on the frequency of stomata. So if you're not familiar with the stomatal frequency approach to CO2, this cartoon will kind of walk you through it. Here is a leaf cuticle. This is the waxy impermeable layer of all leaves. They have breathing pores or stomata that allow CO2 in, water vapor, and oxygen out. And it's a really simple relationship that has been shown by herbarium collections, by growth chamber experiments, that say that under low CO2, leaves will have lots of stomata per unit area. Doesn't matter the species, they will. It'll be calibrated to the species. And that under high CO2, that frequency or number per unit area decreases tremendously. And it's this inverse relationship that leads to the stomatal frequency approach. And the stomatal index has been shown over and over and over again to be mostly sensitive to CO2. So here is a ginkgo cuticle from the TJ boundary. It shows the stomata amongst a sea of epidermal cells. Just explains stomatal index, the number of epidermal cells that are stomatal. So for the TJ, this is results of the deviation from the late Triassic values across that TJ boundary. And you can see that for both a extant ginkgo species as well as an extinct benatite species, that those values, stomatal index values, half across that boundary. If you use nearest living equivalent plants to calibrate the CO2, that means that it was a doubling of CO2 across that boundary. And on the right is the red curve is a loss multi-regression through 900 estimates, and it suggests background values pre the boundary, about 800 to 1,000, going up to about 2,000 immediately afterwards before returning to background values. What does this mean for rates? Well, we don't have a really good estimate on rates across this interval, but we know it's probably representing about tens of thousands of years, kind of like the other hyperthermals. And that comes up with rates that are 2 to 3 orders of magnitude smaller or longer than are the ones of the present. Another analog that is a bust, but lots to be learned. So what can we learn that we don't learn from other times? And that's what I want to look at now. Stomatal index you just looked at, CO2 proxy. This is now the size of the stomatal pores. And they co-vary. When the stomatal index goes down, higher CO2, so do the size of the stomata. You won't find this in the literature, short of one paper from the TJ, and one that we're about to write. The point is this goes completely against all diffusion theory for plants. They're not supposed to do this. They're supposed to starve when they do things like this. But they did. And it has huge implications for regional climate, but also for global conditions. So in this case, Stenstadter et al. Took this data, applied it to a gas numerical exchange model to look at what happens to leaf scale to canopy scale transpiration across this boundary. And what they find is about a 50 to 60% reduction at both scales during the high CO2 time. What was most important about this is that it showed for the first time that plants, through physiological changes, but within one plant, an individual leaf, the next generation of leaves can show these developmental changes. Through these physiological changes, they can physiologically force the regional climate, the water and carbon cycle. And so again, just to summarize, go from many stomata to fewer as well as smaller stomata under higher CO2. You reduce the transpiration, and that water has to go somewhere. It stays in the soils. And eventually it becomes runoff. And for the TJ, this might provide that link between the marine and the terrestrial, big changes in biodiversity. That is, surface runoff, excess erosion, nutrient loading of the coastal waterways could lead to eutrophication, maybe even anoxia. But the question is this some fluke thing that no other time period shows? And keep in mind that absolutely not one of the models, climate models, that project the future includes anything that would allow these kinds of things to be modeled. Okay? Vegetation is effectively static. It's one type, one plant functional type, and it migrates with climate. It doesn't developmentally evolve. So the implication, I sort of said this already then, is that understanding this, we aren't going to learn this from the recent past. We are not going to learn it from plant growth chambers, not under present day conditions or recent conditions. But these might actually be more common than we thought. I'm going to show you in the next example. And that these have implications not just for the past, but also for the future. So the third example, last example, I paradoxically turn to the late Paleozoic Ice Age in terms of greenhouse gas forcing. So this Ice Age that we heard quite a bit about yesterday from Tracy Frank, Chris Fielding, Lynn Sorgan, and others who spoke in that late Paleozoic session. Time period that's been long considered the longest lived, most extensive ice age of the Phanerozoic. Argued for a long time to be under conditions of CO2 that were minimally like today, if not lower. And I'm sure they were low. It didn't make sense that they were probably low forever, and that's something we've been interested in addressing. Now I realize this is one heck of a complicated set of diagrams, probably can't read them, but they still illustrate how dynamic of a glaciation history that the late Paleozoic really had. What people like Chris Fielding and Tracy Frank, John Isbell have shown in the last decade is that this was not one long-lived ice age, but it was actually a series of discrete glaciations that were interleaved with times of diminished ice. How diminished? We don't really know. What this diagram on the left shows is a on-lap, off-lap to the right history for the Carboniferous, 30 million years of the Carboniferous, on-lapping in the Donets ramp of the Ukraine. The red stars are high precision ID TIMS dates that we have for this, or we obtained for this section. What you can see in blue are intervals where the off-lap was considerable, basically more than 100 kilometers off-lap, and we attribute this to ice sheet expansion. On the right, you see a map of southern Gondwana in shades of white and blue are sort of the range of estimates we have right now for when and where we had ice during this. The idea being multiple ice sheets rather than one large one. And sometimes they came and sometimes they went, depending on where you were. The obvious question is, and the one that's driven my research group of the last decade, is what was driving this very dynamic ice age or glaciation? And what I'm going to show you now is that we think that changes in CO2 within the range of our recent past and projected for our future was what was driving this particular ice age. So one of the biggest challenges, other than the data model discrepancies, certainly in the deep time, is how do we get at CO2? And the approach we've been trying to take is a multi-proxy approach. There are different proxies. Many of them are getting better. They still have lots of error associated with them. But the idea is if you take a multi-proxy approach to reconstructing CO2, you start to see where they converge and what is noise and what might not be, and then address what is the role in forcing these climate transitions in this ice house. So we are using 3 different approaches to reproducing CO2. The first one is the one that's probably been most widely used in the deep time, and that is the paleosol carbonate paleo-CO2 barometer. It basically takes the C13 values of carbonates and their associated organic matter. This is from a fossil soil, for instance. Puts it into a model that runs a little more complicated than this, but this is generally the input parameters. And there's a lot of uncertainty, in particularly associated with the multiplier. That's been a real Achilles heel. Just this past year, Dan Breeker put together a MATLAB code. If you haven't seen it and you're interested in this, phenomenal code that takes all of our different people or groups, all of our new methods to constraining these input parameters, integrates them, and also propagates their errors. So the results you're going to see is using that MATLAB code. So here is the best estimates. These are interval averages. The interval averages are sub-100,000-year averages. Actually, they're sub-20,000-year where we have that, the sampling opportunity. And so the interval averages, there are 2 standard error around those averages. For 10 million years of the mid to late Carboniferous, what you can see immediately is this white interval. That's the uncertainty. They still remain high. But if you look at these values, and this is a 3-point running average, really just to sort of train your eye, it's not necessarily fully meaningful, but you can see that these are defining clear trends of rises and falls. And many of them are happening on the 400,000-year scale. Some, maybe due to resolution, are on the million or sub-million year scale as well. But they're ranging between about 200 ppm and about 600 ppm. And that's what I mean when I refer to this within the range of our projected future and our recent past. But we knew there was no way we could go with this petagenic carbonate CO2. We did for the early Permian, published that in 2007. But even that has to be revisited in terms of magnitude. So the other way of going at this is to go into the plant-based CO2 proxies. And there now are 2, thanks to a recent model by Franks et al. That came out this year. This first one is the stomodal index, the same one I showed you for the TJ boundary. These are plants from the Carboniferous. The data come from the Illinois Basin exclusively. We tracked these 2 species through this 10 million year period. And here is a photomicrograph of one of these cuticles under epifluorescent light. And I think you can argue, or I will, that the preservation here, 300 million years old, is as good as that at the TJ, if not better. And what you can see are stomatal complexes outlined in yellow within the background of epidermal cells. And if you're wondering what T is, those are the bases of hairs. These were actually very hairy plants, which probably comes into play climatically. Stomatal index, you'll see the results of the stomatal index calibrated to CO2 in a coming image. These were calibrated, by the way, the CO2 by using 3 nearest living equivalent tree ferns. The other plant-based model just came out a month ago, is one by Franks et al. It allows you to take these stomatal traits plus a few other cuticle measurements, as well as the carbon isotopic composition of your cuticle, and apply it to a model. This is a very simplified version of it. It's written for R. It simultaneously solves for 2 equations. But the bottom line is what it does is it assumes that the plant physiology will respond to CO2 in such a way that CO2 can be solved for if you can constrain the AN, which is the CO2 assimilation rate, and the total conductance of the plant. And we can do that with the stomatal traits and the carbon isotopes. So a third way. So let's look at how they compare. On your left is how they compare. You saw the red curve, the red points, that's the paleo CO2 pedogenic paleobarometer values. And in green are the values for stomatal index using the nearest living equivalents. In orange are the results of the Franks et al. Model. So you can see that generally, actually all of them follow the trend. When low is low, so are they. However, they're riding higher by about 100 ppm than the pedogenic carbonates. And that's something that we're still kind of looking at. But where they do converge, they fall very nicely, including being able to, and you can barely see this, but define the exact same rises, but in higher resolution than the rises that were defined by the pedogenic carbonate barometer. So we're very confident that these rises are real, the ones that are defined in multiple intervals. And they are happening. If you cross over to the Donitz sea level curve, again, I remind you, on-lap to the left, every one of those rises corresponds to on-lap, sometimes very large on-lap, and the lows correspond to these last gasps of short-lived glaciation before going into the very large glaciation at the close of the Carboniferous and early Permian. So values that range between 200 and 600 parts per million within the range of our projected future, with rates, however, that are even slower than those of our recent. So we've been investigating the CO2 climate glaciation linkages using climate models, and these are the results for a totally coupled atmosphere, ocean, 3D ice sheet and biome model. What these show is for 3 eccentricity cycles, so the effects of orbital forcing over different CO2. At values under 300 parts per million, you get big ice sheet. And you get ice in the northern hemisphere, for which there is no longer any evidence that it existed. When you go to 840 parts per million, you are almost at the point of losing all your ice. And for the sake of Tracy and Chris, I'll sneak in here that these models produce ice first in eastern Australia and western Argentina because of the moisture effect, and then elsewhere, and that's what the geologic record seems to support as well. But for here, it's these values between 300 and 800, for instance, at 560 parts per million, where the model produces multiple ice centers with small to medium-sized ice sheets. And it's only these ice sheets that can wax and wane sufficiently to make the sea level changes that are reconstructed from the successions at this time. Those models also show the evidence of orbital forcing and CO2, the sensitivity of the CO2 on the vegetation. So here we're looking at a low CO2 world. You can see the predominance of, in green and blue, those tropical and warm temperate forests. And they are increasingly replaced when you raise CO2 by what are the dry land desert vegetation, and about 850, and you lose those forests completely. High latitude in the low CO2, very much dominated by tundra. So let's look at what happens in terms of the orbital forcing when you're looking at summer low insolation or insolation minima, tundra dominated. You end up having strong vegetation climate feedbacks, particularly here in the high latitudes. These are all albedo based. So increase in albedo as you have in these low summer insolation, temperature, big change, decrease, and you get ice expansion. So we know from the models that vegetation climate feedbacks are incredibly important, but the only ones we've looked at so far are just those high latitude albedo related ones. Take the summer high, the insolation maxima, you're shifting your vegetation from tundra to the boreal forests and barren land, and you see a decrease in soil moisture, a shift from latent heat flux to sensible heat flux, and of course temperature increase, and then ice melts. But what I really wanted to get at, lastly with that example, is those vegetation climate feedbacks. Those albedo vegetation feedbacks at the high latitudes are just the tip of the iceberg with regard to this ice house, and with huge implications for our climate models of the future. So we've been asking, this is sort of something we're working on now, it's a 5-year project, very collaborative by botanists and modelers. Could tropical vegetation, through physiological forcing, in response to an initial change in CO2, could that physiological forcing create more climate change regionally and perturbation to the water and carbon cycle? So paleobotanists have long known for this time period that there are major biome shifts that certainly, like the ones shown by the models, this is a typical lycopsid swamp that dominated the low latitudes during the glacial times. The lower diorama is what the vegetation looked like during the interglacial or higher CO2 times. There's still these big telephone pole sigillarian lycopsids, but dominantly you get tree ferns and other kinds of less dense canopy. These are your opportunistic or your weeds that favor seasonal climates. But what we've been noticing is that, in fact, if you look at a single species and you track it over 10 million years, there are changes in the leaf anatomy, the leaf characteristics, that suggest there was physiological forcing of climate at that time, analogous to the Triassic-Jurassic. So here you're looking at stomatal number. Remember, low CO2 is high number of stomata against stomatal size. And this positive relationship says that when you had high CO2, fewer stomata, they were also smaller. This is that thing that goes against plant diffusion theory. This isn't supposed to happen, but it is, and it happened in the TJ, and it's happening here. So maybe it's more common than we've been thinking in the past. Like I said, for the TJ, this means we get decreased water vapor to the atmosphere during elevated periods of CO2. The last slide on this, I don't want to get bogged down in, but I do want to make a point that there are other lines of evidence for this going on, and they just haven't been investigated. And so here is one where you're looking at stomatal index in a reverse scale against the carbon isotope values of those same cuticles. Carbon isotope is the black dots. And the point is that they inversely covary, and if you take that along with the changes in the stomatal size I just talked about, it means that those that were forming during low CO2 times, these blue bars, they were conducting like mad. In fact, one of my paleobotanist collaborators says they were like fire hoses. And then when CO2 was higher, they clearly were conducting less. And we see that in the N-alkane, or biomarker fraction, of a subset of those plants, shown here in this total ion chromatogram for the nonpolar lipid fraction. Over here, you see the hydrogen isotopic composition for some of those plants through the low CO2s, high in white, and so on. And you can see those shifts in hydrogen isotopes as CO2 goes up. So bottom line is, once again, they're saying decreased conductance and transpiration with high CO2. The N-alkanes in particular suggest that this was actually a drop in relative humidity. And most importantly is that implication. And we're now putting these into ecosystem scale models and then into global models, but to address things like, could these have actually enhanced regional soil moisture and led to major global changes in continental surface runoff? And the recent literature, modern and future projection literature, is starting to ask these questions. The models are saying, ooh, this could really make huge differences. But I'm going to remind you that there is not one climate model out there yet that can take the land component, the biomes, which are effectively plant functional groups. Those are fixed. None of them can vary and then do this physiological forcing. That has to be put into those models. So to come full circle and wrap up, last couple slides, I want to go back to then looking at a comparison of emission rates of CO2 versus time scale of emission on an exponential scale for these time periods of greenhouse gas forcing that I just talked about. The glacial minima of the Carboniferous icehouse, the PETM and TJ boundary of the Mesozoic, Cenozoic greenhouses. Also shown on here are Permian through Miocene periods of high volcanic CO2 release, including the large igneous provinces. And and then I guess I have to tell you what these are. These stars are projections for CO2 over the next couple of centuries based on the current rates of 2 to 3 parts per million per year. And I don't think there are many who think about this a lot who wouldn't say that those are too low of rates given the onset of long-term positive feedbacks. But clearly, there is no overlap whatsoever in those in terms of emission rates. So what it says, what we know, and what Carlotta said yesterday, we don't have analogs. But the focus needs to be not that we don't have analogs, but rather what can we learn from the non-analog worlds that we can't learn from the recent past, including the Pliocene. And in this particular case, we've learned that the magnitude of carbon being released is geologic scale, yes, but it's that unprecedented rate that guarantees us, based on what we've learned from the deep time, that once you look at the impact of short-term feedbacks, and you add the onset and acceleration of the longer-term feedbacks, and acceleration being the key thing there, what might happen in terms of processes, climate processes, and ecosystem response. So I'll end with, or summarize with, kind of a repeat of what I said, but just to sort of hammer it home. Yes, they are non-analog climate states. The Pliocene is too. That's an equilibrium warming. It is not the transient world we are in. What can we learn from them? Whether they're ice houses under CO2 forcing or greenhouses, the deep time record has shown us now repeatedly that there is insight into fundamental climate processes, often involving these complex feedbacks, and more importantly, that the models aren't yet capturing right, leading to these data model discrepancies. And those data model discrepancies need to be one of our highest priorities. Not necessarily to resolve the past, but what they can tell us about why those models aren't working. And I know that my collaborators tend to think that it may even be in the physics of the models, not just the processes. And lastly, I didn't say a whole lot about ecosystem response, but for the paleobiologists in the room and others, obviously the deep time is our only archive of the ecosystem response and those things that we call critical ecosystem thresholds under this evolving and high CO2. So thank you for listening.
very inspiring talk. And we are kind of running out of time, but if there is maybe time for a couple of very quick questions, comments. Okay, otherwise, Isabel will be around until Friday. So I guess you can always, there is a question there, I'm sorry. Sorry, I didn't see you.
I was intrigued by the interpretation of the stomata as a function of evaporation. You refer to a less humid world during high CO2.
So it's not that the stomata are responding to a less humid world. I mean, they might be, but it's their influence on water conductance. It doesn't matter. The background world could be a big drop, a small drop, whatever is leading. It can be an irradiance thing. I mean, it's a lot of factors that will change that stomatal size, right? And less so be the density. But it's the fact that when you put those changes into gas leaf exchange models, it's the impact of what they do on conductance.
Okay, well,
Can I answer that one?
Yeah, you can.
Could you go into the Holocene or something like that? Have you seen any changes in relative sizes that might back up the theory that you're saying?
So, no, it doesn't, and that is actually kind of part of my point. Diffusion theory, so his question was, do you see any change in the Holocene that would back up this? No, you don't at all, and that's because you wouldn't expect to. What we're working on now is the very idea that that would be red noise effectively. That's not enough forcing on the system. And that's probably why it hasn't happened. People have looked at like angiosperms since the Cretaceous. At the scale at which they've seen them, they haven't seen those changes. But you go into those short-term events, and that's where it's starting to show up.
Okay, now I'm afraid we have to move out because the other sessions are starting. So thank you very much again.